Frictional electricity. When we rub two objects vigorously, a force called friction resists the relative motion of surfaces and generates electric charge. Therefore, the electric charge generated by friction is called frictional electricity. Since this charge is produced only at the place of friction and it remains still on the object, therefore it is called static electricity. How long does this charge remain on the object? Let us find out. Take one plastic comb, rub it on your dry hair, and bring it near the pieces of paper. It attracts them. Now again rub the comb on your dry hair, and this time wait for a few minutes. Bring it near to the paper pieces. What do we see? We see that this time the comb does not attract the paper pieces. Why does this happen? This is because electric charge remains on the object only for a short duration. Do all objects get charged by rubbing? What do you think? Yes. But the success of such experiments depends on how are these experiments performed and which weather they have been done in. The air surrounding us always has water molecules in it, especially in the rainy season. These water molecules present in the air absorb the electric charge present on the object. Therefore, we should perform all experiments of static electricity in dry weather, particularly in winter. Let us perform an activity to understand the properties of electrical charges. Activity. Let us first take few straws, a plastic bottle with cap, and a woolen cloth. Let us now take a plastic bottle and place a straw on its cap. Now take another straw and bring its one end near the end of the straw placed on the cap of the bottle. Do we observe any movement in straw? No, we do not see the straw moving. Record the observation in the observation table. When an uncharged straw is taken near the uncharged straw, there is no repulsion or attraction seen. Thus, we can say that electrically uncharged objects do not attract or repel each other. Now, leave the straw on the cap as it is. Let us rub another straw against a woolen cloth. Now take its one end near the straw on the table. What do we observe? We observe that when the straw is taken near the straw kept on the cap, the straw kept on the cap moves towards the straw in hand. Record this observation in the observation table. When a charged straw is taken near the uncharged straw, we see the uncharged straw getting attracted towards the charged straw. Thus, we can say that an electrically charged object attracts an uncharged object. Now, remove the straw on the cap of the table. Rub this straw and the straw in hand against the woolen cloth at the same time. Keep one end of the rubbed straws on the bottle. Take one end of another straw near it. What do we observe? We observe that both the straws move away from each other. When two straws carrying similar charges are brought near each other, there is repulsion between them. Thus, we can say that, like electrically charged objects, repel each other. Now keep the rubbed straw on the bottle as it is. Let us take the woolen cloth on which the straw was rubbed and bring it near the straw. What do we observe? We observe that the straw moves towards the woolen cloth. That means, when the straw is rubbed on the woolen cloth, the charge opposite to that of the straw is developed on the woolen cloth. Record this observation in the observation table. When a charged straw and the oppositely charged cloth, which was used for rubbing, are brought near each other, there is attraction between them. Thus, we can say that, unlike electrically charged objects attract each other. In this activity, we have seen that not only do unlike charges attract each other, but one charged and one uncharged object also can attract each other. Therefore, attraction cannot be considered as the sure test for identifying an electrically charged object. Hence, repulsion is used as a test to identify an electrically charged object. We have seen that unlike charged objects attract each other, and like charged objects repel each other. Let us observe this phenomenon with one more example. Let us take a transparent plastic bottle and fill it half with mustard seeds. You will find mustard seeds in the kitchen. Remember to get your mother's permission first. Let us shake the bottle vigorously for few seconds. Let us now observe the bottle carefully. What do we see? We see that mustard seeds try to move away from each other but stick to the inner surface of bottle. Why does this happen? When we shake the bottle vigorously, the friction between mustard seeds and the plastic surface generate opposite charges on seeds and the walls of the bottle. At the same time, like charges are generated on seeds. Therefore, the seeds repel each other, whereas the seeds and plastic surface having opposite charges attract each other. Instead of mustard seeds, you can also use tiny thermocol balls to see this effect of static electricity. Till now, we have seen that objects can be easily charged by rubbing. Can we charge objects by methods other than rubbing? Yes, there are other methods. Let us learn about them by performing some activities. Activity. Let us learn the method to charge an object by contact through this activity. Let us first take a plastic comb and rub it against a paper. Now touch this comb with another uncharged comb. Let us take the other comb near some pieces of paper. What do we observe? We see that the comb attracts pieces of paper. How has this happened? When we rub the comb against a paper, the comb gets charged. When we touch this charged comb to another uncharged comb, electric charges get transferred from charged comb to uncharged comb and make it charged. That is why it attracts pieces of paper. This method involves contact between a charged and an uncharged object. Therefore, it is known as charging by contact. Let us now perform the next activity to study the method called induction. Activity. We shall learn the method of charging an object by induction with the help of this activity. First, let us take a plastic comb and rub it on dry hair. Now take the rubbed comb near a thin trickle of water from a tap. What do we observe? We observe that when the rubbed comb is brought close to the flowing water, water gets attracted to it. Why does this happen? When we rub the comb against dry hair, the comb acquires a negative charge, whereas at first, the flow of water is not charged. When a negatively charged comb comes near the flowing water, the negative particles present in the water nearest to the comb are pushed away. That part of the water trickle now becomes positively charged due to a deficiency of negative charge. The comb has negative and the water has positive charge. Due to the attraction between these opposite charges, the flowing water is attracted towards the comb. The action of electric charges, which takes place when two bodies are brought close together, is called electrical induction. Now let us draw the comb away from the trickle. What do we observe? We observe that when the comb is taken away, the negative particles in the flowing water come back to their original position, and positive as well as negative charges become equal in number. As a result, the water becomes uncharged again and stops getting attracted to the comb. Thus, from this activity, we can say that by induction process, we can charge an uncharged object by simply bringing it near the charged object without making a contact. Always remember, the number of positive and negative charges are equal on an uncharged or neutral object. The electric charge generated by induction stays only as long as the charged object is near to it. Look at this boy who is rubbing an inflated balloon on his shirt and sticking it to a wall. Why does the balloon stick to the wall? When we rub a balloon against cloth, it gets negatively charged. This negatively charged balloon, when taken near the wall, there is induction. The negative particles present on the wall where the balloon is held move to the other side and the surface of wall becomes positively charged. This positively charged wall surface gets attracted to the negatively charged balloon and the balloon sticks to the wall. After learning about the generation and transfer of electric charge, let us do an activity to understand the effects of electric charge. Activity. Let us first take a spent tube light and a thin polythene bag. Now make the room dark. Let us rub the tube light with a thin polythene bag carefully. What do we observe? We observe that the spent tube light starts glowing. Why does this happen? When we rub the outer surface of the tube light by a polythene bag, static electricity generates. This illuminates the fluorescent material present on the inner surface of the tube light. Thus, the electric charges generated by rubbing make the tube light glow. Let us study the effect of electric charge by performing one more activity. Activity. Let us take a small aluminium ball and hang it freely with the help of a thread on a stand. Now charge an inflated balloon by rubbing it on a cloth and bring it near the aluminium ball. What do we observe? We observe that the aluminium ball gets attracted to the balloon. Why does this happen? The negatively charged balloon generates positive charge on the aluminium ball by induction, and both the objects get attracted to each other. Now touch the balloon to the aluminium ball. Do you see something different? Oh yes! The aluminium ball, which was earlier attracted to the balloon, now goes away. Why does this happen? When we touch the balloon to the aluminium ball, both the objects become similarly charged. As we know that like charges repel each other, hence the aluminium ball goes away from the balloon. After studying the effects of electric charge, let us now study how electric charges can be detected using a device. Gold leaf electroscope. Gold leaf electroscope is a simple device to detect the electric charge on an object. It consists of a copper rod which has a metal disc at the upper end and two thin gold leaves at the other. Let us understand the working of a gold leaf electroscope. First bring an uncharged object, say a glass rod, and touch it to the disc. What do we see? We see that the gold leaves remain closed, which means the object has no electric charge. Let us charge the glass rod by rubbing it on a cloth and touch it to the disc and see the difference. What do we see? We see that the gold leaves move away from each other. Why is this so? When a charged object is touched to the disc, both the leaves are charged by the same electric charge. These similar charges repel each other. That is why they move away from each other. Now touch the disc with bare hands. What do we observe? We observe that the leaves collapse. Because when we touch the disc with bare hands, the charge in the leaves goes into the earth through our body, and the leaves get discharged. We have seen that gold leaves are used in the electroscope. But can we use leaves of some other metal instead of gold? Yes, we can use leaves of metals such as aluminium and copper instead of gold in an electroscope. Remember, the metal that we use should be a good conductor of electricity and should be malleable so that it can be converted into a thin sheet. Great scientists. In 1752, Benjamin Franklin conducted an experiment of flying a kite with his son William. The kite was made using deodar wood silk cloth instead of paper, as it would not tear with wind and rain, and a metal wire. The metal wire was joined in such a way that its one end was at the top of the kite and the other end was joined to the string of the kite. There was lightning in the sky on the day they flew the kite. When the metal wire touched the clouds, the electric charge got transferred from the clouds to the kite. Then, the loose string of the kite became taut, and the electric charge reached the earth through the string. A spark was seen when the string touched the earth. Thus, he showed that lightning is a form of electric charge. Electric charge present in the Earth's atmosphere are called atmospheric electric charge. Let us proceed to study about it.